Okay, the next presenter is Tangyuma from Princeton University. So he'll be talking about a simple but tough to beat approach for sentence embedding. Okay.
Thanks. Yeah, this is the joint work with Sanjeev, Arora, and Yongyu Liang, and we are all from Princeton University. I'm Tangyuma. So we are interested in sentence embedding. So the goal is to embed a sentence to a vector. So there could be multiple goals, and one of them is that we want the human ratings of the similarity of the sentences, of two sentences A and B, is reflected by the embeddings in the product of V and VB. Right, so V and VB are the embeddings of the word A and B. So maybe you can have other goals, like you want to use these embeddings as features for other supervised learning tasks, like entailment, sentiment analysis, or even similarity task. So, and in this paper, our contribution is that we have a very simple method, which is just a weighted average of the word embeddings in a sentence, plus some removal, some of special directions, and and this simple method seems to perform pretty well. And also, this simple method is motivated from like a theoretical model of the text. The weighting also has connection to TF-IDF and word-to-vect. So, and it beats many basic word embedding methods like skip sort, LSTM, RN, and so on and so forth. Okay, so before talking more about our algorithm, so let's briefly mention some of the previous works that we have done on word embeddings. So with Arora, Li, and Liang, and Ristke, we have a word embedding model. We have a generative model for the text, which tries to explain the existing word embedding method. So the model is like this. So we have a hidden Markov model, and we are thinking that we have some context vector CT at each time t, and this context vector or discourse vector, that's what we call it in the paper. So this discourse vector is moving slowly at every time, and at every time, given the discourse vector, we are going to generate a word. So technically, we have this discourse vector, and we have some embedding for every word. And the generative model for the word given the discourse is a log linear model. The probability of WT given CT is proportional to exponential of the inner product of the discourse time and the vector. So this is quite related to log linear topic model of Min and Hinton. So the motivation to have this model is that it turns out that we can use this model to explain word-to-vect and graph both. So in word, we call in CBOL. So basically, we have that given let's say 5 words, then you want to predict the 6th one. Given now 4 words, then you want to predict the 5th one. And what you do is that you use the average of the word vectors and inner product with the new word, and this is the probability of the new word. And under our model, basically the explanation for this is that this average is basically the best estimate of the current discourse vector under our model. So if you assume that like in this window of size 5, the discourse doesn't change too much, and let's say, and you want to estimate the CT plus 4, if you do a simple calculation, you see that the maximum likelihood estimator is the average of the previous 5 word vector. So so this is the expectation of word-to-vect, and we can also explain graph under certain assumptions on the word vectors. Say we assume the word vector to be like isotropic or close to isotropic, and we can prove that actually if you compute the log of the co-occurrence probability of the two word W and W prime, it indeed has the same form as used in the graph fitting objective. So but if you believe this model, then basically this is saying that okay, maybe we should use the discourse vector as our embedding, and if you want to use the discourse vector as embedding, then maybe you should estimate it using the maximum likelihood estimator. And as I said, that the maximum of the MLE estimator for the discourse vector is just the average of the word embedding. So in some sense, this explains the why the simple average works in some sense. So empirically, a simple average indeed works, sort of works. So okay, so this is just a brief summary of some previous works, and so in this paper we have inspired by the previous one, we have a little bit more realistic and modified model for the sentence. So just for simplicity, we make all the discourse vector the same in this sentence. So basically, this is kind of like a mixture model. You generate a discourse vector, and then you use this discourse vector to generate the words in a sentence independently. However, we changed the generative model for the word given the discourse a little bit. So now we have this a little bit more complicated formula. So let's explain this two terms. So the first term is kind of like a smoothing term. So the kind of rationale is that we found that even when an author is writing something like a car, something about car, then still there's quite a lot of chance to to generate some word that is completely different from unrelated from car, like just for some kind of random reason. So that's why I want to add this kind of a smoothing term to capture this kind of probability, this kind of a background probability that is not relevant to the discourse vector. So and the second term, this is very similar to what we had before. This z sub, this is a typo. The c tilde should be b. So the denominator is just like the partition function, and this exponential of this, we have this exponential of the word vector and a vector bs. So what is bs? Bs is a shifted context vector. So this is another kind of a correction term. So Bs is a combination of some special direction and the real context vector. So again, similar to the rationale before. So because we did an experiment, we found that in these word embeddings, often you have some systematic bias towards some direction that we don't exactly understand, and it sounds like those directions corresponds to either syntactic things or some common things. So and those are not quite helpful in the for the similarity task or for entailment task. So we want to separate this kind of common part or the syntactic part from the real semantic part. That's why we introduced this BS, which is the combination of the common thing and the semantic thing. So this is our new generative model, and then this model, we are going to use CS as our embedding. And so what we're going to do is that we're going to, have an MLE estimator for the CS, for the BS first. So what we do is that we take just the log likelihood, and with some simple, mathematics, and we can find that the best estimator for the BS, for the shifted context vector, shifted discourse vector, is the weighted average of the word vector. And I think I have some typo here, but it's not super important. So, and then we use the shifted vector to estimate, the real semantic vector CS. And what we do is that we recall that BS is just some C0 plus some scaling factor times CS. So basically what we do is that we want to remove this contribution of C0. And what we do is that we take the top left singular vector of all vectors in BS in the whole task. And then we remove that direction by just projection to the orthogonal subspace. And that will be, the CS hat will be our final sentence embedding. And so just let me briefly mention the relationship to other weighting schemes. So in TF-IDF, the weighting is logarithmic of 1 over the PW. By the way, PW is the word frequency of this word W. So this is not exactly the same. So our form is something like a ratio, I think I made a mistake. So this is A over A plus PW, my bad. So we don't have log, but in the TF-IDF, there's a log. But it turns out that our one is indeed doing better than TF-IDF by like 5%. So it sounds like probably our theory is more accurate, or it's a little bit better than TF-IDF. This is also kind of similar to word2vec actually. So in word2vec, the vanilla version is that you use this average of the word vector and the inner product with the new word vector and take exponential. That's the probability, and that corresponds to the update rule, which is that if you take the gradient, if you ignore the partition function, the gradient will be just the average of the word vector. However, in the actually in the paper, they have some sampling technique to simplify this computation of this average. And the sampling technique is that we are going to sample the word vector according to some function Q of W, and this is only depends on the word. And this sounds like it's just a trick to speed up the computation of the average, but actually it also changed the expected value of the update. So, and if you compute the expected value, it's just the weighted average of the word vector. So, so that's why it's kind of like we have the same kind of rationale as word vector, and it turns out that even also in word vector, this weighted average is important to get some boost in the accuracy. Okay, so and also we tested this empirical this weight scheme compared with our weight scheme, and it sounds like they are quite similar empirically, even though the form is a little bit different. They have some square root of 1 over the probability. Okay, so finally let me briefly mention the experiments. So I guess so this is a big table. Maybe the most important thing is the last 5 column. So this column is the average. We just use the average of the glove vector, and this one is the weighted average with the TF IDF weight. And there is some PSL vector that is trained in the previous weighting et al.'s paper. We also took that and take the average, and the last 2 columns are the weighted average using our scheme. And we see that so our ones is often like several percent more than the unweighted average case. And this is some experiment on the classification task. Okay, so the one above is on the similarity task, where you just take the inner product of 2 sentence vector embedding, and you measure how correlated this value from the true label. And the second one is that you do some supervised learning task using the embedding, and we see that we can do better than other RN LSTM on at least 2 tasks: the similarity task and the entailment task. I guess I'll stop here. Thanks.